Hi class, in this video I want to introduce a very important statistical concept called the normal distribution. So in this section and also in the next section we're going to talk about this distribution in just very general terms. But if you ever take a more advanced statistics course, you will spend a lot of time jumping into or learning in much more detail about the normal distribution. Okay, so we have a bunch of objectives actually in this lecture. First one is we want to recognize characteristics of normal distributions. Then what we want to do in number two is we want to understand what's called the 68, 95, 99.7 rule. This relates to normal distributions. The third thing is we want to find scores at a specific number of standard deviations from the mean. This is going to be something called a Z-score. Then we're going to use this 68, 95, 99.7 rule. And we want to go back, just as I was kind of talking about under objective 3, we want to convert a data item to a Z-score. We want to understand this concept of percentiles and quartiles. We want to use and interpret margins of error. And then the last thing we'll do is spend a real quick brief thing talking about recognized distributions that are what we call not normally distributed. Okay, so what is a normal distribution? So you might have heard this called the bell curve. Like if you look down here, you can see this kind of looks like a bell. So it's called a normal distribution, is referred to as the bell curve or a Gaussian distribution. So normal distribution is bell-shaped and symmetric about a vertical line at its center. So what this vertical line means with it's symmetric is if you were to take the distribution and cut it in half and fold the two sides on top of each other, it would be mirror images of each other. Okay, the other awesome thing about a normal distribution is those three measures of central tendency, the mean, the median, the mode, they are all equal and they're all the same. So for something that's normally distributed, the data, the mean is equal to the median is equal to the mode, and they all occur at the center of the distribution right here. So what you can kind of see here, what this is showing is this is talking about the heights of men. Okay, so think about the heights of adult men. So if you were to take a random sample of 100 adult men and construct a histogram, it might look something like this. Okay, and this is what the whole concept of a normal distribution is. The majority of observations will be kind of centered at the middle of the distribution, right around the average height. There'll be fewer people who are much taller than the average, but there are people who are taller than the average, and the same thing on the shorter side. As you continue to increase the sample size, so say you go from 100 men to 200 men, you'll notice that the curve, the histogram becomes more like this bell curve down here. If you interview, I don't know, 1,000 men, 10,000 men, look how close this distribution looks like a bell curve. So when you see a histogram of a data set that looks like this, what that's telling me is that heights of adult men follow this bell curve shape, right? So they're saying that this is the normal distribution for the population of heights. So the thing about the normal distribution is what I have here is I have three different graphs and they all kind of look like a bell curve. Okay, they all do. But the shape of the normal distribution depends on the mean and standard deviation. So these three graphs here have the same mean because they're all centered at the same value, but different standard deviations. So what happens is as the standard deviation increases as it gets larger, the distribution becomes more spread out. Okay, so it gets like shorter and wider with a larger standard deviation, but it retains its symmetric bell-shaped curve, meaning for each of these, you could cut the curve in half and fold it over on top of each other, and you'd still get the same thing on each side. Okay, so related to the standard deviation, we have this rule called the 68, 95, 99.7 rule, and it goes like this. Approximately when something is normally distributed, so this only works for normally distributed data. So it says approximately 68% of data items fall within one standard deviation of the mean on both directions. So suppose you have this normal curve here, all right? For whatever reason, the average is 0. If you take one standard deviation and add to it and one standard deviation and subtract it, this area right here, what we're saying is 68% of data values will fall in this shaded area right here. You can go on. If you take two standard deviations, so go 1, 2 standard deviations above the mean and 1, 2 standard deviations below the mean, it turns out that 95% of the data will fall between the 2 standard deviations above the mean and 2 standard deviations below the mean. You can go even further. If you go out 3 standard deviations above and 3 below, what you're saying is 99.7% of data falls from -3 standard deviations below the mean to 3 standard deviations above the mean. Very, very powerful to be able to say that. Okay. So going on, if I want to talk about finding scores at a specified standard deviation from the mean. So male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches, right? Let's find the height that is 2 standard deviations above the mean. Well, no, we want to find 2 standard deviations above the mean. Well, if you take the mean and multiply 2 times whatever the standard deviation is, so the mean is 70 inches and the standard deviation is 4 inches. So if you go 70 plus 2 times the standard deviation, well, that's just 78 inches. So a height of an adult male 78 inches, that adult male is 2 standard deviations above the mean. All right, so let's talk about using this 68, 95, 99.7 rule. So let's use the distribution of male adult heights in the figure to find the percentage of men in North America with heights between, let's say, 66 inches and 74 inches. Well, if you look, mean is 70. If you subtract 1 standard deviation, which is 4 inches, you get 66. If you add 1 standard deviation from 70, you get 74. So look at this. This is 1 standard deviation above, 1 standard deviation below. So this 68, 95, 99.7 rule states that approximately 68% of the data items fall within 1 standard deviation, 4 of the mean 70. So if you take the mean minus 1 standard deviation, you get that 66. You take the mean plus 1 standard deviation, you get that 77. And we are seeing that, just as I said, 68% of males have heights between 66 and 74 inches. Awesome. All right, let's talk about Z-scores now. So what a Z-score does? As a Z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. So all a Z-score formula is it can be obtained by using this formula. Z-score is equal to the data item minus the mean divided by the standard deviation. All right, so data items above the mean have positive Z-scores, and data items below the mean have negative Z-scores. So the Z-score for a mean, whatever the average of a data set is the average minus the average, well, that would just be 0. So it's just the data item minus the mean divided by the standard deviation. So the mean weight, let's do an example. Okay, so computing Z-scores. So the mean weight of a newborn infant is 7 pounds and a standard deviation of 0.8 pounds. All right, so the weight of newborn infants, we were told on, is normally distributed. So let's find the Z-score for a weight of a baby that's 9 pounds. Well, we know the mean is 7 pounds and the standard deviation is 0.8 pounds. So the Z-score, we'd write Z sub 9, so that's telling me the Z-score for the value of 9 is the data item minus the mean divided by the standard deviation. So this is just 9 minus 7, which is 2. Okay, so that's the data item minus the mean. If you were to take 2 and divide it by the standard deviation, 0.8, you get 2.5. And that's it. So all this is saying here is this: if a baby is born that weighs 9 pounds, it is 2.5 standard deviations above the mean. That's all that's telling us right there. All right, let's do another one. So intelligence quotients, all right, these are IQs. All right, on this specific intelligence test, we know are normally distributed. Okay, so the average intelligence test score is normally distributed with a mean of 100 and standard deviation of 16. So what is the IQ corresponding to a Z-score of negative 1.5? Okay, well, the negative sign negative 1.5, right, tells us the IQ is 1.5 standard deviations below the mean. So the score is the mean minus the number of the value of the number of standard deviations times whatever the standard deviation is. So the mean is 100 minus 1.5 standard deviations below. Well, the standard deviation is 16. So 1.5 times 16 is 24. So 100 minus 24 gives me 76. So the IQ corresponding to a z-score of negative 1.5 is an IQ of 76. All right, let's talk about percentiles and quartiles now. All right, so percentile. If n% of the items in a distribution are less than a particular data item, we say the data item is the nth percentile of a distribution. So for example, what that means, if somebody says, oh, what is the 90th percentile? All right, or I'm in the 90th percentile, that means 90% of people scored below them on that particular test or whatever they're talking about. Then we can have quartiles. So what they do is they divide data sets into 4 equal parts, like quarters. So the 25th percentile, okay, so 25% of people below is the first quartile. 25% of the data fall below this first quartile. It's the same thing. The 50th percentile is the second quartile, and the 75th percentile is the third quartile. That's all they are. Okay, so let's talk about a percentile interpretation for z-scores. So using the z-score in a table, all right, and we'll do this in the next section, you can find the percentage of data items that are less than any data item in a normal distribution. So in a normal distribution, the mean, median, and mode all have a corresponding z-score of 0 and are the 50th percentile. So what we're seeing here is thus 50% of the data items are greater than or equal to the mean, median, and mode. So half the data values in a normal distribution are above the mean, and half are below. All right, let's move on and do a talk about polls and margin of error. And you probably have seen this. You know, if you pay attention in the news, you've seen a political poll of some type, and they always resort or tell us the margin of error. So statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening. Okay, so like, why is it okay when we get a poll that says, 40% of people support this, or 100% or 80% of people support this thing? If you take a statistics class, you'll dig deeper into why. But polls are never 100% accurate. There's always what we call a margin of error. So if n is the sample size, so like if you talk to 1,000 people, okay, there is a 95% probability that the value of the population parameter you're trying to estimate lies within 1 divided by the square root of n of the true population statistic. So this plus or minus 1 divided by the square root of n times 100% is what we call the margin of error. All right, let's take a look at this example. So in a random sample of 1,172 children ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. Like if your parents boss you around, 17% of these kids say it's bad. Well, that was only a sample of 1,172 kids. Okay, so does exactly 17% of all children think getting bossed around is a bad thing about being a kid? Probably not. So the poll probably made like a little bit of an error. Okay, so what is the margin of error here? So the sample size n, they talked to 1,172 kids. So the margin of error, just following the formula, take plus or minus 1 divided by the square root of n. Well, 1 divided by 1,172, and then times that by 100%, you get a margin of error of 2.9%. Okay, so let's talk about next, write a statement about the percentage of children who feel that getting bossed around is a bad thing about being a kid. Well, this is what we're saying. Look, I don't know what the real value is, but there is a 95% probability that the true population percentage lies between. If you take the statistic you got and subtract the margin of error, you get 14.1%. And if you take the statistic you got, the 17%, and add the margin of error, So what we're saying is I'm 95% sure that the real value is somewhere between 14.1% and 19.9%. Okay. Last thing, let's just talk about other types of distribution. So this graph here represents the population distribution of weekly earnings in the United States. Okay, so there's no upper limit to weekly earnings here. Okay, so the relative few people with very high weekly incomes pulls the mean income to the greater value than the median. So the most frequent income, the mode, occurs actually to the left on the low end of the data items. So when you have this tail that shoots off to the right, this is what we call the skewed distribution. And this is because a large number of data items are piled up at one end or the other with a tail to the other end. So this graph is what we call skewed right. So you can also have skewed left. All right, thanks, class.